start and start. Okay, so today we are actually almost finishing the chapter of gravity. Gravity is a short chapter, and the next two chapters is also quite short. So what we will probably do today is to just discuss the potential energy of some gravitational object for extended bodies, and then we will spend the remaining time to do some tutorial questions. Okay, so let's talk about the gravity due to extended bodies. So this chapter will involve a bit more math and integration, so be prepared. But otherwise, the concept is pretty much the same as what we've been doing before, right? So what we have been talking about since previous classes is that we always been assuming that the gravitating masses, right? We only look at the center of mass, and we just take the mass and we take the distances between the center of mass. So we actually ignore the sizes, right? So usually when we talk about a satellite orbiting the Earth, or Earth orbiting the Sun, some planet orbiting another planet, then when we calculate the Newton's force, right, Gmm over r squared, the r is actually should be the distance between the center of mass. Although when distances are very, very far away, right, this size is very small compared to r, then it's pretty much approximately the same as well. So in other words, right, we have been assuming that we ignore the shape and size of the object. We just look at the point mass and then we calculate the force. So in the previous class, we have been calculating the force of the object, and then we know how to get the direction, right? If you're looking at for this small mass, then the force is having this magnitude and the direction is being attracted toward the other mass. And from there on also, we have learned how to calculate the potential energy, right? So this is what we have been learning in the previous classes. Yeah, I lost my hair. Yeah, so so now we have been assuming everything is a point mass. Then what we want to address now is the slightly more complicated problem. Firstly, right, I should also say this: is this assumption true? When we are assuming that this is a point mass, assumption true. Okay, so it is true for uniform and spherical masses. Okay, so if it's uniform and spherical, then yeah, the assumption is true. So what we are going to do is, if the object is not spherical, then what's going to happen? So how about non-spherical bodies? Okay, so let's say, right, my object, right, my gravitating mass is some general shape. Okay, and how do we calculate the gravity because of this? So the second object is, I will still consider some small point mass object of mass m, right? And how do I calculate the force experienced by this object? So as you can see, right, this is a bit more of a more difficult problem. So let us see how to address this situation. Okay, yeah, so having short hair is actually very cooling and safe on shampoo. So so let us try to calculate this. So how is this more difficult, right? Because this mass, right, is a big object. So let's say this is having big mass big M, this is having mass small m, right? And because gravity is a distance dependent force, then we can easily imagine, right, this section will have having this distance away from the object m, so it's going to cause a gravitational attraction. But another portion will have a further distance, so the effect will be very, very different, right? So for example, this part, right, and this part, so this part is nearer to m, but this part is further away. Okay, so let's say this is R1, this is R2, and because it's different distances, right, even if you choose a mass of a same mass, then this part will have a stronger attraction compared to this. So how can we calculate the force of gravity because of this situation? Okay, so let us see how to do this. Okay, now firstly, right, again, we have been doing this many times already. When we were calculating the center of mass, moment of inertia, what we do is we look at the infinitesimal mass, right? Consider many points, one infinitesimal mass, we try to get the expression, and then we do the integration to get the final result. Okay, so we are doing the similar method over here. So let us first, before we answer this question, right, let us try to calculate the potential due to multiple point masses. Okay, so let's say I have a point mass. Okay, so let's say I have point mass, and I will call this big mass M1, and then I have M2, and then maybe I have M3 that is further away. So what is the potential acting on M, right? So the first point mass is having this distance R1, the second point mass is having the distance R2, and this one is having the distance R3. Okay, so R3. Then what is the potential energy at M? Potential energy at M. Okay, so the potential energy at M is, well, I'm focusing on this potential. So for a single source, it is this formula. So the total potential energy is going to be G. Then because of this mass M1, it will have this potential energy, and then the second object will give you a second potential energy, and the third object will give you a third potential energy, right? So for every distance, you contribute a certain potential, and then you just add up all the results. Okay, so hopefully this one is very obvious and straightforward to everyone. Okay, basically we just sum up the effects of different objects. So generally, for any number of masses, for n gravitational sources, okay, so I got M1, I got M2, and then M3, dot. There's many M, right? So many M, and then what is the gravity on M over here, right? So if I have many gravitational sources, right, so what is the gravity affecting here? Okay, so the total potential energy is what? Well, the total potential energy is just to sum up everyone. So the first mass over the first distance, the second mass over the second distance, and everything. So basically what we are doing is a summation of I from 1 to n, Gm, then the mi, because different mi have different mass, and each of them have different distances, so I do the summation over this. Okay, so this is a gravitational energy for point sources. Okay, so that is pretty simple if we have multiple point sources. So what we are going to do if we want to talk about extended body, so gravity due to extended body. Okay, so we are going to do the same thing. An extended body is just a sum of many infinitesimal points. Okay, so let's say I have some extended body, and then my total mass is m, right? And what is the gravitational potential energy on m2, right? So we do the usual thing, right? So we do the usual thing as we did for moments of inertia and center of mass. Is like we consider this as a sum of many points, right? So many points. We look at one point. Okay, so we look at one point first, and then once we get a formula for any arbitrary point, we sum up. That means we do the integration. Okay, so this one point is having distance, some distance r from m. Okay, so then we say that the potential, we calculate the potential first. So in this chapter, we focus mostly on potential because make it easy for you guys. For forces, right? For forces, it's a vector, so you need to do vector, and then it's so troublesome. So focus on potential first. Okay. So potential energy due to one infinitesimal point dm, right, is this. So generally for an object of mass m, right, the potential energy is gmm over r. So this is the potential. If my mass is large, the potential energy is a bigger number, the magnitude is larger, right? But if my mass is small, then it will be small also. So if this is an infinitesimal mass, I want to say that they will give a small infinitesimal potential energy. Okay, so I got G, and then the mass is m is fixed here, but I want to talk about infinitesimal mass, dm. Dm, yeah, should be big M, capital M, over R. Okay, so this is for 1 point. Then the total potential energy is the sum due to all points. And because it's these are infinitesimal, so if I summing up infinitesimal quantities, it becomes like a integration. Okay, so again, like calculus. Okay, so I think by now, right, this is week 10, so by now you have already learned integration already, at least definitely learn about the Riemann sum, right? So it's the, now you know it's the same idea, we have been doing it. So the total potential energy is just the integral of all the infinitesimal contributions. So what we are doing is we are integrating gm then dm over r. Okay, so this is the formula that we are going to use. Okay, so any questions so far? Or campus cannot get haircut. Wow, that's... We assume R is the same for all points on the body. No, that's why that is the reason why it's difficult for extended body, because R is not the same, right? So for this portion, R is small, and then this portion R is big. So that means R is a variable, and it is an integration variable. So we integrate for the different distances of R. Okay, so yeah, we will see in the example later. So it's integration. It's not a constant. Yeah, right. Yeah. So I have seen, you know, in quizzes and exam, a lot of students always take things out of the integral, assuming they are constant. We shouldn't do that for R. Okay. Can I? Yeah. So let us see how we will solve this question over here. Okay, so let us look at one example. Yeah. So simple example is, again, we are looking at rod. Right, so by now I think rod is our best friend. We have calculated the center of mass of the rod, we have calculated the moments of inertia of the rod, and then now this thing. So let's look at this. Uniform rod of mass m and length l is placed along the horizontal axis such that the left end is on the origin. Okay, so we got this thing here, same situation as last time, but now we are calculating the gravity. Okay, so a point mass is placed in this location along the horizontal axis. Find the potential energy experienced by mass m, and then find the force, if x is not much greater than L. So how do we solve this? Okay. Okay. So let's solve this. This is example 7.3.1. Okay. Example 7.3.1, we are talking about the uniform rod. So uniform rod is, well, my rod looks like this. This is the origin, okay, and I have a rod of mass, total mass is big M, and then this is my x-axis, and then I have a small m located over here. Okay, so we do the usual thing as follows. So we look at one infinitesimal mass, right? So this is dm, and then the length of this is a small section is dx, since we are talking about the x direction. So let's talk about dx, right? And then so there's a few x's here. Okay, so this is potentially very confusing. Now the position of small m is something I will call x. Okay, so something I will call x, and then this is x equals to 0, and this is another position of this section of the rod. So this section of the rod, right, I'm going to call this x prime. Okay, so this just to remind us that there's two different distances over here. So I'm talking about so firstly, right, I have an infinitesimal mass that is dm, right? And then if this position of dm is x prime, so position of dm is x prime, and then position of m is just x, is just x, right? And then I want to calculate the potential energy. So potential energy is this formula over r. What is r? R is the distance between m and dm. So what is the distance between m and dm? So it's from here to here. So this is the r that I want. Okay, so be careful, because every student, a lot of students will make the mistake where they just immediately put in r just like that, and put in x, right? Put in x, but that's actually wrong. What I want is the distance between the masses, and this is r. And what is r? Well, as you can see, right, this distance is just x minus x prime. Do you agree? So do you agree? Yeah, so let me check. Yes, agree, right? Okay, yeah. Yeah, okay, good. So if you agree, then the rest should be okay. Let us try to perform the calculation. So this is page 2. This is page 3. Okay. So firstly, let's look at the infinitesimal first. From here, we are solving part A first, right? So the potential energy of small m due to just this section first. We are only looking at one point, and then later only we integrate. Okay, so the expression for du is, the general formula is this m and then times the infinitesimal m over r. And as I have said, right, it is gm dm, and then the distance, this r is x minus x prime. Okay, so it's x minus x prime. Okay, so then the next thing that we want to do is, okay, we, as usual, there is a dm over here. So what we want to do is we need to substitute an expression for dm. So how to get dm? This is a uniform rod. Just a review of what we have always been doing many times for a moment of inertia. For a uniform rod, right, dm over the length is a function lambda, but if it's uniform, then this lambda is a constant. So what we can do is, well, we take dm is equals to lambda dx, right, and then the total mass is big M. So big M is just the integral of dm. So in other words, big M is integral of lambda dx, and since this is a constant, I'm integrating this with respect to dx, right? And then what is the limits of integration? This is, again, every time you need to be careful when you set up your coordinate system. This is x equals to 0, and then this last part is x equals to L. So I'm integrating from 0 to L, and this is where we get m is equals to lambda times L. So I conclude that lambda is equals to m over L. So once I got m over L, right, I put this back into here, and I have get the expression that dm is just m over L dx. Okay, so yeah, I don't know whether this is very boring to you guys now or whether I should repeat again, right? Since I don't know, yeah, so if you are, whether you are still comfortable with doing this type of integration or not, yeah, I know this is something that we need the practice. Hopefully we get a lot of practice about this by now. Okay, so now I got the expression for dm. Okay, so we can now put this into here, so that my du is equals to negative, well, let's see what we have, g m, and then we just put the whole thing over here, so I've got big M over L dx, and then divided by x minus x prime. Okay, and then now once we got the du, then I can easily get the total potential by integrating both sides of the equation. So let us simplify our expressions. Okay, all these are constants, so I can take it out. So I got g big M and then small m, and all these constants I take out, and then my integration is integration with respect to oh yeah, so one important thing I forgot. I was saying x prime is the position of this infinitesimal mass, and this is all about the infinitesimal mass, so I should say this is x prime. Okay, because the x is just the position of m, so it's nothing to do with this dm. Do you follow so far? I think my mistake might cause some confusion, so let you process this first, right? So I'm talking about dx prime. So there's two different variables here, x prime and dx prime. So hopefully you guys can follow. Okay, so my variable of integration, this is my variable of integration. Okay, so let's see. Because the dx is for dm, yeah, exactly, correct. Yes, that's what I meant. That was my mistake. So should have a prime there. Because dm is for x prime, and then this is just x. Okay, follow so far? Any question? No? No question? So okay, so as you can see, right, definitely we cannot assume R is the same for the whole body. So that was your question, right? Yeah, so previously we did assume R is the same for the whole body. I guess to make it more precise, previously we did assume that, but it turns out that it's only true for uniform spherical body. So now we are not assuming. So now we do not assume these are constants. So we integrate and see what is the result, right? So this is the potential for one section, but what is the contribution of all the points? So all the points contributing a potential energy will be obtained by integrating from the first point to the last point, so from 0 to L. So let us integrate this function from 0 to L and see what we get. Power of mathematical manipulation. Yes, exactly. Yeah. Right. So let us integrate this. Okay. So this one also, again, speaking of power of mathematical manipulation, we also have to be careful. With great power comes, we need to take care of the minus sign in this case. So great responsibility. There's a minus sign here. Okay. There's a minus sign here, and then I integrate this, right? So my variable has a negative and 1 over this. So do you know how to integrate this? This is a ln, right? Logarithm. Okay, so there's a logarithm with a minus sign. So only with the minus sign, after you differentiate, you get the correct expression over here. Okay, so this is from 0 to L. Okay, and always remember, this is, again, careful, my integration variable is x prime. So if you substitute the limit, right, you put the limit here, not here. Okay, you put the limit here. So let us put this limit in. Okay, well, first of all, there's two minus signs, so they take care of each other. So I got GMM over L, and then yeah, we substitute in the limit. So the front limit is x minus big L, and then the lower limit is just 0, so I got ln x. Then I can simplify again, GMM over L. This is ln x minus L over x. Okay, and then I got simplify this one more step. I got GM over L, and then the logarithm of 1 minus L over x. So this is my potential energy due to the rod and the point mass. So I have a rod, right? Yeah, so imagine some object in space that having a mass of big M and is actually a rod of length L, and then you have a spaceship of mass M at the distance x away. So this is x equals to 0, this is x over here, and then the gravitational potential energy is given by this. Okay, so this is my gravitational potential. So this rod will exert a gravitational force, and we will calculate the force in the next part, but firstly we got the potential energy already. Okay, so let us see whether is this a positive or negative number. So let us check the x, right? Well, x is larger than L, so this is a positive number that is smaller than 1. 1 minus something that is smaller than 1, so it is a positive number lesser than 1. So it's like 0 point something. So logarithm of 0 point something will give you a negative term. So it's a negative potential. It's still negative potential energy. Okay. So let us calculate the force next. Okay, everyone following so far? Am I recording? Test. Recording, yeah. Must put the negative sign first before integration. Yes, well, yeah, and the negative sign, the original negative sign, because it came from our definition of potential energy, right? So all here got negative sign because our potential energy is defined with the negative sign because of here. So the negative sign follow us all the way until here. What was the other question? The energy is always due to the force direction. Energy is a scalar, and later, yeah, so the force direction is, we will do this as usual. So df, f is negative du dx. So the direction will come from the slope, whether it's a positive gradient or a negative gradient, and then with the negative sign. The integral from 0 to L is for what? What do you mean? 0 from L? Yeah, from 0 to L, right? So we need to add up the whole thing. Just like the moment of inertia and everything. The moment of inertia rod, we still integrate from 0 to L. So it's the same thing. The positive or negative of the energy. Yes, so the way we define potential energy is always negative, and then it's always negative. So it's just the definition of potential energy. Yeah, it's just negative. That is for finding the dm of total mass. Yes. Yeah, because you integrate from 0 to L, then you get the total m, right? Total m is lambda times L. Okay. Okay. Yeah. So actually, right, regarding energy, as we can see, right, the physically relevant quantity is the differences in potential energy. So whether the potential energy absolute value is negative or positive, right, we actually care, given a potential energy function, we only care what is the changes in potential. So usually, generally speaking, for other systems, whether it's positive or not, it doesn't matter. And by convention here, we define it to have negative sign. So yeah, that basically that's about it. Okay. Okay. Any other questions so far? Okay. So if no question, then let us find the force. Okay. So I have the mass m. What is the force experienced? The gravity of the force of gravity experienced by small m. As you can see, right, this is a rod and it has no y direction. So it is symmetrical about the y direction. So there's only the x component of the force, right? So the force, right, if you recall, force is by right it should be a vector, right? And it has a x component, and it has a y component, and it has a z component, right? And then the x component of the force is negative, differentiating with respect to x, and then the y component is differentiating with respect to y, and then the z component is differentiating with respect to z. Okay, so we got this, but then from here, right, we see that our potential energy is independent of x and y directions. So function u is independent of y and z coordinates. Okay, so it's independent of y and z coordinates. If I differentiate, then I will just get 0 and 0. Okay, so which is to say that I have no y component and I have no z component. Agree, right? Can we say the potential energy is negative because m? No. Yes. Well, I mean yes and no. It is negative, and it is the reason why work is done to attract m towards itself, right? Is that the potential energy is lower nearer the source compared to further away. Okay, so yes, so it's not really because it's negative. It's just that the value of the potential energy is lower here compared to here. So if I plot the graph, right, it's going to be something like this. So nearer the source, the potential energy is lower. So then and then the reason why, if this is lower, right, then by the definition of this force du dx, this type of shape of potential will try to attract objects towards this direction. Okay. Okay. Yeah. Can yeah. So it's because of the slope of the graph rather than actually the value. Okay. I will come back to this later. Let us finish solving this. So the y and z components are 0, so these two terms are 0. Then this one is differentiating with respect to x. So let us calculate the x component. So x component is, there's a negative sign. So again, there's another negative sign, so we have to be careful, right? So negative sign and then differentiating with respect to x. For the physics students haven't taken calculus 2 yet, right? Yeah, partial derivative. I have used this earlier, but don't be scared. You have also been using this in thermodynamics. It just means differentiating that particular constant, and you don't care about anything else. So that is all it means. Okay, so I'm just differentiating this function. And this function here, everybody are constants except x. So actually it's easy to differentiate. Right, so these are constants. So I got gmm over L, and I just need to differentiate a logarithm. Okay, so let's try to differentiate this. Okay, so my fx component, well, all these are constants, so I can put it in front, and then differentiate ln. So differentiate a logarithm, this thing goes down, so I got 1 minus L over x, and then differentiating negative L over x. So this one is, again, must be careful with the minus sign. So differentiating L over x, so what do I get? So I got gmm over L, and then I got negative L, differentiate 1 over x, I just get negative 1 over x square. Am I right? So I got this, and I got 1 minus L over x. Okay, chain rule, right? Well, the doesn't have to, I mean, yeah, not chain rule, but the differentiation. Okay, differentiated 1 over x, I got a negative sign. So I got 3 negative sign. In the end, you just need 1. Okay, so gmm over L. Actually, there's a L to cancel this, and then I got 1 over x square, 1 minus L over x. So this L will cancel, and then I got gmm over x square, 1 minus L over x. So this is the force along the x direction. So we got Fy equals to 0, Fz equals to 0, which is why the force experienced by M is only having this direction. Okay, but yeah, so physically also, even if you don't know the equation, right, you look at this picture, right, you look at this picture, it's just, obviously it's only pulling in the x direction. And as you can see, right, there's a negative x direction, so the attraction is to the left, towards the origin. So if I put my coordinate system here, then going towards here is a negative direction. So this is the correct direction of the force. Like this. Okay, any question? Let's see. Yeah, so I'll leave it here, and then I'll read the question here so that you can continue looking at this. Teams. Wait, it's very slow. What is the antiderivative of a log function? I don't remember. You can do it by integration by parts. Yeah. Partial derivative in thermal, right? Yes, because it's, you cannot escape. Because thermal you have different variables in the same function all the time. You have to do partial derivative. Learn partial derivative by yourself, or I think for these two courses, right, for the moment, just partial derivative is, if it's x, you only differentiate x. If it's y, you differentiate y. So actually there's nothing complicated, right? So let's say I have a function f, I have a multivariable function, is I think I showed you this before, right? X square y, right, plus sine y. Did I show you this before? How do I partial differentiate this with respect to x? Very easy, right? You just look at x. So it's just x, y. And this one has no x, so it's like a constant, so it's 0, right? So you got this. And then I partial differentiate y, right? Then this is y power 1, so it will just become 1. And then this becomes cos y, okay? And then you can do the higher derivative as well. So partial derivative f with respect to x, right? That means you just differentiate again, but still x, so I get 2y. In fact, I can mix partial derivative. So I take this and differentiate y. So I partial differentiate this with respect to y. Wrong notation. So let me do it here. So partial f, partial y, partial x. So it becomes 2x. right? How to partial differentiate 1 over log x? Thermal many symbol more complicated. Oh, okay, so I will answer this soon. And then this one also, right? I can partial differentiate the second time. So differentiate with respect to y again. So this one will be gone. Then this becomes sine y. And then I can take this and differentiate x itself. So I partial f partial x. Okay, so let's see what we get. Right, so if I differentiate this, I get 2x. And there's an important theorem about partial derivatives is that notice that these two are the same. So there's a theorem about partial derivatives. Partial f partial x partial y is equals to partial f partial y partial x. Okay, so this one will come in very useful even for thermal, because thermal, this will give you the Maxwell relations. Yeah. So how to differentiate this? Well, it's here. So it's here. Okay. How to differentiate this, right? So differentiate logarithm. Differentiate logarithm is 1 over this and then continue this. Actually, it's not even partial differentiate. It's just normal single variable differentiation. From calculus 1. It's over here. Wait, I can't, not clear on the phone. Most of the math you learn is not a math class but physics class. Yeah, you know why? Because physics, you need to immediately apply the advanced math. So we need to rush to apply the advanced math for the basic physics. That's why you learn a lot of math now, because we have to, right? We need to use it. But the math class is slowly build the foundation and rigorous theorems so that you are stronger for later. Yeah, all these foundations. About the df dx, just consider which variable including x. Correct. So for partial derivative, right, it's like differentiate this and pretend the other one is a constant. Okay, so for example, if this case, right, what does this mean? So this means differentiate y, then pretend x is a constant. Then this one is the other direction. So differentiate x, pretend y is constant. The d. For partial derivatives, you write the curly d. This is understood for partial derivatives. The straight d is for single variable derivative, and it's not really a personal preference. Is the reason why will be will come in more advanced mathematics. So because in the future, this will avoid confusion in the future. For now, it's like everything is differentiation, so it makes no difference to us now, but we should get used to this, because in the future it will become important. Yes, the straight d is for exact differential, NT6. Yeah, correct. So it's like the 6 upside down. Yeah, and in fact there are many symbols for derivatives, like, and all these are like very scary. You will learn this in like graduate school or whatever. There are many different types of like different derivatives. So, but don't worry about it now. Okay. Any other question? actually, yeah, we've been spending quite some time talking about this, but let us try to finish the question. This last part is actually interesting. Find the force if F is much greater than L. So we have found the force, okay? So I only have the X component, so I got GMM over X square 1 minus L over X. Then according to the question, right, if okay, so if, what was it? X is much greater than L. So if X is much larger than L, so this symbol means X much larger than L. Okay. Then if X is much larger than L, what happens to L over X? So I have a number divided by a huge number. So that means if L is a small number and X is a very large number, if I take L divided by X, I'm dividing by a large number. So this is very small number. So it's much smaller compared to 1. Do you agree? Right? So it's small number compared to 1. That means 1 minus L over X is negligible. Is approximately 1. Okay, so 1 minus a small number is still pretty close to 1. Right, so what I'm trying to say is, therefore, in other words, if X is much larger than L, the Fx is approximately GMM over, this thing is almost like 1, so it's just like X squared. And this one, right, is like back to Newton's law. Okay, so what it is trying to say is that for X is much larger than L, right? So if X is much larger than L, then I have a rod of length L, but my X position is very far away. So X is much larger than L. So if something is very far away, right, then the shape of the rod also is no longer important. It's almost like a point mass again. So that is why we come back to this original equation again. Yeah, sort of much larger than L. Yeah, that's true. Okay, so then I come back to this equation. So this is one way to check whether your answer is correct or not. Okay, so you got the answer, you're not sure whether it's correct, but it should be consistent with other situation that you know. So I have a rod, because when my X is near to the rod, right, then it's what I said just now, right? The different parts of the rod will exert different gravity on M because the distances are different. But if you are very far away, right, you zoom out. If you zoom out, the different distances on L is very negligible compared to the total distance. So if you zoom out, everything looks like a point mass, right? So something very far away, like the back of the rod and the front of the rod is no difference. It's just R. And this is the situation where you can ignore the shape of the rod, and like was it Kai Shen who asked earlier, we just treat R as the same because it's so small, right? It's negligible. The differences are negligible, so you just treat it as 1R. Okay. Any question? What time is it now? Okay. So now, if there's no question, let's go on to the next example, which is the gravity due to a uniform ring. Okay, so this is our next example. Yeah, no need to manipulate the ocular. Just look at this example, right? We have a uniform shaped ring of radius A, as shown in this figure. So let me draw while I read the question. So this is example 7.3.2, a uniform ring, right? So a uniform ring is a shape of radius A. So having radius A, right? And then a particle of mass m is placed at a distance x from the center of the ring. So from the center of the ring is like this. along the line through the ring center. So this is a line through the ring center perpendicular to the axis of the ring, like this. And then my point mass m is over here. Point mass m is over here, right? And then we want to calculate the potential energy of the system. So how to calculate? So this is a uniform ring, and we do our usual thing So this is an extended body. So let us look at one section, and this part is actually quite easy. So this section has infinitesimal mass dm, and the length is very short, so we call it ds. And this is a uniform ring, so we say that dm over the length is the mass per unit length, and this is a uniform, so this is constant. Okay, so if dm is a constant, then let's see what happens. So this is lambda ds, right? So lambda ds, and then to get the total mass, m is the integral of dm, which is to say that m is integrating lambda ds, and lambda is a constant. Integrate this with respect to ds. Okay, so for this question, right, lambda is a constant. I take it out, and then I'm integrating ds. Integrating ds is just calculating the circumference. Can you see? This is just the circumference. So what is the circumference? 2 pi a, right? So 2 pi a. So my m is equals to lambda 2 pi a. Therefore my lambda is m over the circumference. Okay, so from here, so I got my expression for lambda. I can put this back into here, so that my dm is m over 2 pi a ds. Okay, so we will use this later. Why is it negative here? Oh, I know what you mean. In the earlier version of the is this the earlier version? There was a typo. There was a wait. It's correct, right? It's negative. Yeah, this is the corrected one. So it's differential. So differentiate, yes. Yes, Kaishan is correct. Differentiate this. So there's a negative sign here, and if you differentiate 1 over x, there's another negative sign. Yes. So this is one negative, and then remember, if you differentiate 1 over x, it will give you another negative. Okay, so if I differentiate 1 over x is negative 1 over x squared. Okay, so if I differentiate negative L over x is negative L, so it's negative L. Yeah, correct. 2 negative will become positive. And then there is another one still in front. This 2 negative will become positive. This one is from the definition of potential energy. Okay, wow, almost 11. So let me quickly do this before we take a break. How to find this potential? Well, I want to find the potential energy, right? So the potential energy at m due to dm is what? So the infinitesimal potential energy is always g small m times this m over r, right? So you just need to find the expression. This is mass m, and then the distance is from here to here. R. So this is dm, this is m, right? So the potential energy is this mass times this mass over R. Then you need to figure out what is R. So this is, maybe you must be careful, right? So the length from here to here is R. This part is radius A. Okay, so this is a three-dimensional picture. This is a right angle triangle. So can you see that how to get a formula for R? The distance is x squared plus a squared. Square root. Right? The potential is also negative, so there's 4 negative. 4. Yeah, because I got a typo. So this is the one after I corrected the typo. I uploaded in, did I upload it in Moodle? I uploaded, but maybe I forget to click save. So this, let me upload again, and I will remember to click save. Yeah, sorry about that. Because this is a right angle triangle, right? It's a three-dimensional picture. Okay, so if you make it easier to imagine, let's look at this dm, and then the distance here is, so this is a right angle triangle. So I'm just like turning this picture up, then you get this. So every point on this circle is at a distance of x squared plus a squared away from this M. Right, I have a circle and then I have a point right on top of it. So what is the distance? If you just choose any random point on the circle, what is the distance away? It's just right angle triangle. Pythagoras theorem, nothing special there. Okay, so I can put this in now. G M okay, small m, so I screwed this up, so let me do it again. Right, so substitute is m over 2 pi a ds, and then the r I say is this one, right? So it's x squared plus a squared. So let me simplify this. So I got negative g m over 2 pi a, and then ds over a squared plus x squared. Okay, so x squared and a squared, they are both fixed, right? So these are fixed, they are constants. So I can take it out of the integral. So when I do the integration, right, I can take everything out. So this part will again give me 2 pi a. So finally, I will cancel this 2 pi a. So I got g over 2 pi a, 1 over a squared plus x squared, and then 2 pi a. So it will cancel. So my expression now is g over a squared plus x squared. Okay, yeah, so hopefully you can see why right angle, because you just need to get the distance, right? Just try to get the distance and you will use the Pythagoras theorem. Okay, so it's quite late already, so let us take a break for 10 minutes and then we will continue a few more things about this, and then I will do the tutorial 6 challenging questions. So I guess that is what probably what you want to show. Oh, previous page, can. This page and the previous page. Yeah. So let us take a 10 minutes break, and Yeah, we'll come back in 10 minutes. So let me stop the recording first. So there are some interesting question, and actually, right, if you notice, a lot of the philosophical problem that is still unsolved today is always related to quantum mechanics. The Newtonian mechanics, classical mechanics, everything is pretty much straightforward, so there's no unsolved issues over there. But most of them, especially like the determinism and things like that, they come from quantum mechanics, because quantum mechanics has no, like, how to say, yeah, it depends on probability distributions, and why do certain objects follow probability distribution is a strange question, and we still don't know why. So yeah, so there's a lot of interesting ones, and there's one I found yesterday. Where was it? There's one I found yesterday. I put it here. This one is for thermodynamics, and also why do objects minimize quantities, and this one is quite a technical philosophical paper, because I also don't understand much of it. So, but if you are interested, you can take a look, but for now we continue with are you learning QM next sem? Next sem you learn a bit of QM, yes, but the full course of quantum mechanics will be year 2 sem 1. So next semester there's a physics 4 or PHY 104. It's called modern physics. So you learn the early parts of quantum mechanics, like the photoelectric effect, the hydrogen atom energy levels, and some uncertainty principles, and like some basic concept of nuclear physics. So that one is the early quantum mechanics. And then the year 2 sem 1 you will learn the quantum mechanics with the Schrödinger equation, the uncertainty principle, the bracket notation, all that. So yeah, so you'll learn that in next 2 semesters. Okay, so shall we finish off the last question? The last part is to, oh yeah, so the part B, right? So the part B of this question is to if, right? So if x is much larger than a, we do the same thing, right? A over x is much smaller than 1. So my potential energy equation, right, so is given by this. So let me manipulate this. Okay, a square plus x square square root. So usually you want to manipulate until you see something like this, so you can see the terms to ignore. And to do this, right, so what I can do is I can take out a factor of x. So this is x square, right, and then a square over x square plus 1, and then square root, right? So this one is equal to this. I hope you agree. And the square root of x square is just x again, so gmm over x, and then square root of 1 plus a square over x square, right? So this part, if x is much a, then this is approximately 1. Okay, so that means u is approximately gmm over x. So this is again similar to the point mass formula again. So we get this back. E and M, I mean, yeah, don't say right, but it is, well, partial derivatives, right? So if you are okay with that, then fine. So yeah, next semester you will learn E and M and modern physics, quantum mechanics. So these 2 things, right? And yeah, well, maybe it's difficult, but to me at least these 2 topics are more interesting than Newtonian mechanics. So Newtonian mechanics can be hard, as you have said, but the topics itself is kind of boring, right? It's just masses, collisions, and things like that. Speaking of hard questions, tutorial 6. Am I recording? Yes. Yes. Okay. So let's do the question from tutorial 6. The one we are talking about is question 4. Right? Tutorial 6 is here. Okay, so this one. A billiard ball initially sliding on a tabletop. So this is rolling with slipping, not a pure rolling motion. And horizontal velocity is v0, initial is rotating anti-clockwise. Center of mass shown is like this. So this is the situation. And then all the info are given, R and M, some numbers, just call it R and M. And then the coefficient of kinetic friction is mu. So firstly, let us determine the acceleration. And these two parts is probably the tricky one, but I'm hoping to convince everyone that even though it's tricky, right, we just follow SOP, right? SOP meaning we have learned everything like Newton's law, free body diagram, F equals to ma. For the rotational motion is the torque. Tau is equals to I alpha. Just follow that calculation, then we will get our answer. Okay, so as long as you follow SOP, it is also fine. Question 5 is also hard. Yes, I plan to do that next after we do the 2 planks on rollers, right? Yeah, so I will do that next. Okay, so let us, yeah, for question 5, I want to bring props. So I will bring something to show later. Okay, so but first let us do question 4. Okay, this is a sphere, a uniform sphere. So this is the sphere moment of inertia is 2 over 5 mr squared, right, for a sphere. Okay, and then what we have here is initially, right, so I'll draw the initial situation. Initially, this object is rotating this way, but the center of mass is rotating this way. So it is going forward, but it's spinning the opposite direction. So this is not pure rolling, right? So it's rolling with slipping. So rolling with slipping, then there's going to be kinetic friction. Okay, so how do we solve this situation? We draw the free body diagram. So free body diagram, and when we draw free body diagram, it is always good to be clear what is your positive and negative direction. So I'm going to call the right direction to be positive. Okay, so my right direction is to be positive. So what are the forces acting on this object? Well, you can say there is the weight and there is a normal force, but because there's no other thing, right, there's no acceleration in the vertical component, then vertical direction n minus mg is equals to 0, because the acceleration in the vertical component is 0, so n is equals to mg, right? How about the horizontal? So the horizontal force, there is only the kinetic friction, right? So there's a kinetic friction, and then the direction of the kinetic friction is this direction. Do you agree? Because this thing is rolling against the ground, right? It's rolling against the ground, it's friction. And then even like without analyzing the details, right, we see that there's friction, and then this object is moving this way. So the friction is always opposing the motion. Okay, especially for a ball that is rolling in the wrong direction. Okay, another way to look at it is because my tangential velocity is this direction, my center of mass velocity is also this direction. Okay, and then and friction is always the total net force is to the right, friction is always opposite to their motion, so it's acting to the left. Okay, so what I'm trying to say is that the horizontal force is F is equal to ma, and the friction force is acting to the left, so it's negative F and then ma. Do you agree? Okay, so agree, huh? And then friction is equals to the magnitude, right? The magnitude is mu k times the normal force, and this normal force is given by mg. So my friction force is mu k. Here I'm lazy to write the k downstairs, but you know what I mean, right? So mu km and then ma. Okay, so cancelling this, so my acceleration is equals to mu g, negative mu g. So the acceleration is to the left, so it's decelerating, right? It's slowing down the speed acting over here. So I got the linear acceleration of this object already. Okay, do you follow so far? So this part is still quite easy, right? It's just Newton's law, right? Nothing special. How about the torque? So let us try to calculate the torque. So to get the torque, let me say that anti-clockwise is positive. Right, and what is the torque acting on this? So this N and this mg is passing through the center of mass, so it doesn't contribute any torque, right? The distance from axis is 0, so there's 0 torque here, but there is a torque coming from this thing over here. So the magnitude I have shown you is mu k times mg. And look at this picture. This is a force that tries to give it a clockwise torque. Can you see? So I will use my torque equation. Torque is equal to I alpha. Anti-clockwise is positive. This one will give it a clockwise direction, so it's a negative, right? So negative, and then the torque is mu mg times the perpendicular distance, which is r. Okay, r over here, and then what is the moment of inertia? This is a sphere, so this is 2 over 5 mr square, and then I got alpha. This is a non-pure rolling, so alpha is not equals to a over r, not yet. Okay, but for now, let me simplify the m. I can cancel this, so I can bring alpha as the subject. So the 5 bring over, I got 5 mu g over 2r. So this is my angular acceleration. Okay, so do you agree with the calculation so far? Downstairs xdv. Yeah, the subscript I mean mu k, right? So mu k, fk. I lazy to write all the k. So if everyone agree with this, right, then the rest should just follow. So what are we supposed to answer next? Show that if this one comes to if this is satisfied, then the ball is still rolling anti-clockwise when it comes to an instantaneous stop. So before I worry about the statement of question B, right, we already have the acceleration, so I can determine the velocity and angular velocity. Then once I know how the velocity and angular velocity behave, I can answer any question, especially part B. So part B is talking about when V comes to stop, what happens. So firstly, right, first thing that we want to do is we get the velocities. Okay, so I know the acceleration, so I got the linear velocity. So linear velocity in the horizontal direction, right, positive to the right, I will use this equation because this is a constant. So if this is a constant, if my acceleration is a constant, I can use this equation, right? So this v naught is given here, right, positive to the right, and then my a is a negative mu g, so I got is negative mu g t. Okay, this is my linear velocity. Then from here I got my angular velocity. This is also a constant, because these are just some constant number multiplied with each other, so they are constant numbers, right? So I can use this equation. Okay, so omega, and omega 0 is also given. Initially is anti-clockwise, so it's positive number. Alpha is this negative quantity, so I got minus 5 mu g over 2r times t. Okay, so I got my linear velocity formula and my angular velocity formula. I know how they change over time. So both of them are, the magnitude are increasing with time. Okay, so if you plot the graph of v against t, right? So initially is V naught, and then they are decreasing with time. And then omega is also decreasing with time. Okay, so I'm just plotting this graph, right? Nothing special. I'm just showing you, trying to convince you how the V changes over time and how the omega changes over time. So to actually answer the question, page 7, to actually answer the question, let us read it again, right? So show that if this is true, the ball is still rolling anti-clockwise when the center of mass comes to an instantaneous stop. So what the question one is, what happens when the center of mass comes to an instantaneous stop? So when V0. So when V0, I want to show that the ball is still rolling anti-clockwise. So I look at the omega, and anti-clockwise means it's still positive. So what question B is asking us to do is that question B is to when center of mass stop, this means the V equals to 0, show that the ball is rolling anti-clockwise. What this means is show omega is positive when V is equal to 0. That is all it says. So during this time, right, I want to show that at the same time omega is positive. Okay, so is it positive? Right, so let's figure out during this time. So when is V equals to 0? So when, right? So when is V equals to 0? When V is 0, that means according to the formula, V naught minus mu g t is equal to 0. So this is the time where my center of mass becomes 0 during this time. So this is the time V0 over mu g. So during this time, my center of mass becomes 0. Okay, so during this time, is omega still positive or is it negative? So let's try to figure this out. So during this time, what happened to omega? Okay, so my omega formula is omega minus 5 mu g over 2r, and then the t, and I want to know what happened during this time. So during this time, so I put in this time and see what happens. So omega is omega 0 minus 5 mu g over 2r, and then during this time is v0 over mu g. So I cancelling this, right? So omega is omega 0 minus 5v over 2r. And we want to answer the question, is this positive during this time? Okay, so let's try to say, is it positive? So I want to ask the question, 5v0 over 2r, is this positive? And then we rearrange a bit. So I will rearrange omega 0 greater than 5v0 over 2r, or in other words, v0 is smaller than 2 over 5 omega 0r. Wait, is it correct? Did I make any mistake? Yeah, 2 over 5 r omega. So yes, right? So we conclude that if v0 minus 2 over 5 r omega 0, then omega 0 minus 5v0 over 2r is positive, so it's still rolling anti-clockwise. Any question? What time is it now? I'm recording and I'm recording. So clear? Do you know what I'm saying? Okay. So at the time when the center of mass is instantaneously stopped, so V0 is decreasing and then it hits 0. So once V0 becomes 0, right, what happens to my omega? So my omega is given by this formula. So is this positive or not? So this is this one minus this one. So this term will be positive if omega is larger than this number, right? If omega is larger than this number, or if this number is smaller than omega. So this number will be smaller than omega, making it positive if this is satisfied, right? So if this is satisfied, then this combination will be smaller than omega, right? So if this is satisfied, that means this minus this will be a positive number. Okay. This is the tricky part. So no one asking question. There are two possibilities. Either everyone understand or everyone still don't understand. Right? So usually when someone asks question, we can kind of get that, yeah, everyone is following the situation, so they know what questions to ask. If no question, it's either everyone understand everything or understand nothing. So that is the dangerous situation. Brain short circuit. Yeah, I know. So that's why this is the tricky part, right? That's why I slow down here a bit and let you digest this sequence of calculation. I want to show omega is positive, right? Even if you don't understand these last few steps, just remember, how do we convince someone that this number is positive? Or when will this be positive? Will this be positive? How do you make it positive? After a while, the ball rolling will become clockwise. Actually, no. That is the next part of the question. So we will see, right? So when we move on, we will address this situation. Will this become clockwise or not? Okay, so basically, right, what we have shown is this. So again, let me plot the graph of V against T. And then we plot the graph of omega against T. Right, so V was given by V0 minus mu GT. And the starting point is V0, right? And just look at this graph. This is a negative slope with a T. So it's a negative slope. And then we have shown that, just plot this function as a math function, right? It will become 0 here. Right, so we have found that this becomes 0 at this value. So this value is T equals to V naught over mu G. Right, and then let's see what happens here. So I want to see the value. So on this graph, we are supposed to plot omega as omega minus 5 mu G over 2R times T. And basically, we have shown that this is still positive. So so this graph, right? Yeah, so let's see what happens at V0 over mu G, right? So this graph, the slope depends on mu G and R and omega 0, right? So for different omega 0, you get a different starting point, okay? And then this is a downward slope, okay? So it's a downward slope. If omega is large enough, then this downward slope will still be positive when I reach this point. If omega is high enough, right? I want omega to be high enough. Okay, so if omega is, it must be high enough larger than this. So if omega is too small, right? If omega is too small, then my graph will intersect at the negative region, so it will become anti-clockwise. The rotational axis is is the center of mass. The rotational axis here is the center of mass. Okay. Yeah, center of mass. What time is it now? Okay, so 10 more minutes, but we should probably go on to part C now. Yeah, any more questions can ask me later. But what is the part C saying? Part C, right, we just want to describe the motion if, so this one is just to continue the story of part B. So assuming this is satisfied, that means assuming it's still rolling anti-clockwise, describe the subsequent motion. Okay, so let us describe. Now, we have shown that the center of mass, when the center of mass is instantaneously at rest, right? So at this time, omega is still positive. So still rolling, ball is still rolling anti-clockwise. This one is nothing new, it's just repeating, summarizing what we did here. Okay, but what happens is still anti-clockwise. So still anti-clockwise, right? That means when the ball is instantaneous at rest, it's still rotating anti-clockwise. When it's still rotating anti-clockwise, that means it's still scraping the floor in the original direction. That means the kinetic friction is still acting to the left. Okay, so its kinetic friction is still acting to the left, right? Because it's the same as just now. So kinetic friction still acting towards left. Okay, so in other words, still acting towards left. What is this causing? Omega continues to decrease because of the kinetic friction. Is a clockwise torque, so it will decrease the omega. And then the V, right? So the V will become negative. So V continues to become negative. In other words, increasing speed towards the left. Right? So because of the kinetic friction, right, the omega will decrease, right? And then the linear force will make it instantaneously stop, but there's still kinetic friction, so it will cause it to start moving to the left. Okay? So it will start moving to the left with increasing speed, but omega continues to decrease in magnitude because it's a kinetic friction, it's a torque. Okay, so what is going to happen is, well, basically, right, r omega decrease while the linear speed center of mass increase. Then if this two keeps on happening, right, then it will eventually reach a point where V is equals to r omega. If this happens, then what happens? This will become pure rolling. So it will become pure rolling where the rotation is still anti-clockwise. It's just the magnitude is small but still anti-clockwise, but the linear speed is to the left. Okay, so it will. So that means what happens is we are throwing a ball that is spinning in the wrong direction. So I throw a ball spinning in the wrong direction, right? Spinning in the wrong direction, because of the friction, it will scrape the floor, right? It will scrape the floor and then it will continue to spin back, right? So if I throw a ball in the wrong direction, it scrape the floor and then it will spin back. Can you imagine this situation? It's like I think it was Zuru who mentioned, like I think as a kid you can play like spinning the coin, right? You have a coin, you put it, and then if you push the coin the correct way, it will spin to the front a bit and then it will continue to go backwards. So this is this situation over here. Okay, so we have to continue before we run out of time because there's another difficult question coming next, right? What time is it now? 7 more minutes. So yeah, if not clear, you can rewatch the video in slow motion later or ask me again later, but we have to solve. So the last part is, yeah, determine the time when the pure rolling takes place. Okay, so we have known what is going to happen, right? So the speed will increase to the left, the omega will decrease as time goes on. So it will arrive at a situation where V is equal to R omega, then pure rolling. So when will pure rolling takes place? So pure rolling takes place when the center of mass speed is R omega, right? So as we have shown you, right, at the later time is when it's going to the left. So I put a negative sign, the negative direction. So V is negative, so I put a negative so it will become positive. So this equation is satisfied. And then omega is already positive, so I got R omega. And then my expression for V, right, my expression for V is V0 minus mu gt. And my expression for omega, we have got it just now, is omega 0 minus 5 mu g over 2r times t, right? And then just find for t. So negative V0 plus mu gt is equal to R omega 0 minus R and R cancel here, so I got 5 over 2 mu gt. And then I bring this over, so I got 7 over 2 mu gt is V plus R omega. So the time is 2 R omega divided by 7 mu g. Okay, so yeah, question 5. Also hard, right? Yeah, so it is the hardest question. Even now also still playing with coins. Yeah, okay, so you can imagine, then I guess you can imagine the situation, right? The coin thing. Yeah. So I don't have any round things around me, so I'll just draw the picture. So for question 6, right, what we have is this. So for question 6, everything is pure rolling. Okay. Everything is pure. Yeah, let me find something. Okay. I got yeah, so I got this, right, and then some platform. So let me find a platform. So I guess show you the top part of it. Okay, what I'm trying to convince you, right, I think most of the misconception when students answer this question is that we should not assume the acceleration of the upper plank and the center of mass are the same, because if you roll one over the other, right, you can, it's not clear, cannot see, it's very difficult to show. The tissue is moving slower than the plank on top. Okay, so if I roll this over, right, the upper part will move faster than the center of mass. So this is what I want to show you. Okay, but I can't. The camera placement is not good. But let us put in the information. So the upper plank is having mass m. Each of these is having small m, and the radius is r. So all the data are given. The big M is 6 kg. The small m is 2 kg. The radius is 50 cm, is it? 5 times 10 to the minus 2. Converting to meter, you get this. These two are cylinders. So the moment of inertia is cylinder, so it's half. For this m, so small m, r squared, because we are talking about mass of the cylinder, right? The big M is the mass of the plank. Okay, so yeah, right? So now let's try to answer this question. The first thing that we want to do is to determine the linear acceleration of the plank and the roller. Okay, now this is pure rolling. Okay, so if you're talking about pure rolling, right, remember what I said last time for pure rolling, and I show you the animation, right? If the pure rolling is where the tangential speed is having the same magnitude as the center of mass speed. Okay, so tangential speed is having the same magnitude as center of mass speed. So when it comes to the bottom, right, these two velocity will cancel each other at the bottom. Okay, but at the top part, right, the V total is equals to what? Is twice of the two velocity, because it's a vector sum, right? So at the top part, when the wheel is at the top, the instantaneous velocity is V, but at the same time the whole center of mass is going to the right also at V, so the result is 2V. Do you agree? Okay, so because V total is 2V, then the total acceleration is dV total dt, so it's 2 dV dt, so it's 2A. Right, so what I'm trying to say is that if the let A be the acceleration of cylinder center of mass, then acceleration is equals to 2A. Do you agree? What time is it now? 11:50. Okay. Yeah, so running out of time, but should I finish or should we continue next class? Do you mind if I finish the question here? Finish, huh? Okay, so finish. For those who wants to go, for those who want to exit, go ahead to exit. You can always watch the video later, but let me finish this before we go. Okay, so so if you leave now, you can watch the video later. Let us solve this question. For those who are following, right, so everyone has no objection that the plank is going at 2A, the center of mass is going at A, so the top part is going faster than the bottom rollers, right? Agree, right? Okay, so agree. Then let us solve this question now. Okay, so let us solve the free body diagrams. So let us begin. Let us look at the cylinder free body diagram. Okay, so what are the forces acting on the cylinder? So the forces acting on the cylinder is vertical. The vertical force we don't care. We want to look at the horizontal acceleration. So there's two forces acting on the cylinder. The cylinder is touching two things. Each cylinder is touching the floor and touching the plank. And this two touching is the one that causes the cylinder to rotate, right? So there's two forces acting on this. Well, there's a plank, right? So there is a static friction between the plank and the cylinder. Okay, there's a static friction between the plank and the cylinder. Okay, and then it is also touching the floor, so there is another static friction between the cylinder and the floor. So there's two forces acting on this. Okay, and why do I draw the two forces in the front direction? Because it is a static friction. Depending on what you do to it, right? Depending on what you do to it, the static friction can either respond by pointing this way or this way, right? As long as you do not break the static friction. So even if I guess wrong, then never mind. If I guess wrong, then the final answer will just give me a negative sign. So it's no problem. Okay, so now that we got this, then we use Newton's law. Firstly, let me say that right direction is positive. So then I use Newton's law. So the net force is equal to the mass times acceleration of this thing. So the net force is F1 plus F2. is equals to mass times acceleration here. So I got equation 1. Okay, so this is the linear motion. And then let's look at the rotational motion. So torque on the cylinder. So for here, let me call clockwise as positive. Right, so let me draw this again. Clockwise as positive. So F1 will cause it to become clockwise. F2 will cause it to become anti-clockwise. Right, so the torque is equal to I alpha. Then what is the torque? The torque is force times perpendicular distance is R. So F1 is giving a clockwise torque, so R times F1. F2 is the anti-clockwise tendency, right? So I got the minus R, F2. Over here. Then the moment of inertia is half m, mr squared, and then alpha, right? But this is pure rolling, so there's no relative motion between the cylinder and the floor. Sorry, right? There's no pure rolling between the cylinder and the floor. So only for pure rolling, we can say alpha is equal to A over R. So I can put this in. Right? So I got RF1 minus RF2 is half mr squared A over R. So I can cancel this factor of R and cancel another factor of R. I got F1 minus F2 is equals to half ma. Right? So I got a second equation. And then actually F1, F2 are unknown. A is also unknown. So I got 3 unknowns. I got only 2 equations. I need 1 more. So 1 more, I draw the free body diagram for the Planck. Right? So free body diagram on the Planck is this. The Planck is being pulled by an external force F, and at the bottom it is touching the two things. So the top part is F1 for the cylinder. So by Newton's third law, if I draw this to be forward at F1, then for the Planck is the other direction, and I have 2 cylinders, so I got F1 in 2 F1s here and here. Okay, so the net force acting on the Planck is the mass of the Planck times the acceleration of the Planck. And then just now I tried to convince you that the acceleration of the Planck is twice the acceleration of the cylinder acceleration, so I substitute this in. And then the Planck is this forward F minus 2F1, and then 2, so I got 2 big M times A. So this is my 3 equations. So I got 3 simultaneous equations, and you can solve the answer already. Okay, so the tricky part is to get these 3 equations, but once you got these 3 equations, the rest is nothing to do with this anymore. Just solve it as any 3 equations. So I will solve it by equation 1 plus 2. So if I take equation 1 plus 2, I will cancel the F2. I got 2F1 is equals to this plus this, so I got 3 over 2 ma. 3 over 2 ma, and then I can substitute this into equation 3. Then I got F minus 3 over 2 ma is equal to 2 big M times A. Then you just solve for A lah. Right, so since we are quite late of time, so let me just go to the answer. Solving for A, I will give you 2F over 3M plus 4M. Okay, and if you put in the numbers, you get 2 times 6, 3 times 2, 4 plus 16. So this is 12 over 30. So the acceleration is 0.400 meters per second squared. So this is the acceleration of the cylinder. And then Planck acceleration, 2a is just 0.8. So this is how we got the answer. Okay, so I got the acceleration already. And then finally, I get the forces. So let's go to part B, right? So part B, using this result, right, I will get the remaining equation will give me F1 and F2. So yeah, I think everyone knows how to do this. So I'll just, to save time, I will give the answer. F1 is 0.6 newtons. F2 is 0.2 newtons. Okay, so these are positive numbers, and which is why I guess it shows that I guessed the direction correctly by doing this. So you can, as you can see, right, these two forces are pushing forward. So when they're pushing forward, can I make sure that it's consistent with my situation? It's supposed to roll in this direction with the plank, right? So you see the upper force. The upper force is 6 Newton forward here. The bottom force is also 2 Newton, but it's in the anti-clockwise direction. So this force is larger than this force. So the net result is this force is stronger. So this will win. So in the end, this cylinder will get pushed in the clockwise direction. Okay, so this is correct. So this is the two forces acting on the cylinder. Clear? Any questions so far? We figure out the magnitude first, then analyze the direction, see whether positive or negative. Yeah, so it's kind of like what we're doing here, right? So I just simply draw the arrow first, and what I'm really looking for is F1, F2, right? So F1, F2 is, the magnitude is something, and then the direction we don't know. So if I get a positive answer, then I know the direction is forward. If I get a negative answer, then the magnitude is there, but the direction is there. Not necessary. So if, right, if you draw the F2 to be this way, then when you get your answer, right, you will find out that you get F2 is negative. So this is how you know that your direction, your arrow is wrong. So you must put it there. Oh, yeah. So yes, this is the tricky part for the direction, right? But what was this question? Okay, so these are static friction because, right, I have a cylinder is rolling on the floor, right? It's rolling on the floor, and then there's a plank on top of it. So it is touching two things, right? So it has a static friction between the cylinder and the floor, and it also has a static friction between the cylinder and this surface. So there's F1 and F2 on top, and these two forces are horizontal because, you know, tangential, at the tangential point both are horizontal, you know. Yeah. Okay, how to analyze the direction of F1, F2? Well, it's just this, everything we are doing here. Okay. Yeah, so we did here, and then F1 and F2 are unknown, right? So we just treat this as equations, and then we just solve the equation, and then we get the F1, F2. How to... Yeah, so equation 1, 2, and 3. Need to observe from the motion. Yeah, that's why I bring all this thing to show you, like this thing. Okay. Any other question? Well, then ask this alternative question now. Does it make sense for F1 to be vertical? because it's friction, right? Every time we do friction, right, it's always parallel to the surface. Yeah, so it can't be vertical, right? Because we have been doing static friction all the time. Like a box sliding over the ground, then the direction is parallel to the surface, and whether it's kinetic or static. Okay. Yeah. Any other question? No, that's what I was saying. I just anyhow draw the direction. It's a guessing. So if I guess wrong, you will get a negative sign in your answer. So what you can do is, if you're not happy with 2 forward, right, because it's just a random guess. So you can guess this F2. Then you try solving the question. You get a negative sign in your F2. Right? So you just repeat everything, but you put F2 here. And then there's no F2 over here. So F2 over here, so then these two must be positive. Right? Both are clockwise now. And then you try to get the answer. So at the end, you will get a negative 0.2. Yeah, I think what you mean is even a more mathematically precise meaning. You build a positive coordinate system, right? So F1 and F2, correct, exactly what you mean here. You build a positive coordinate system to the right, but F1 and F2 are unknown variables. So you just get the solve for F1 and F2 and see whether they are positive or negative. Yeah. Sort of, yeah. Okay. Any more question? Is it clear yet? If not, yeah, maybe Wednesday we can go in a bit detail. Correct. Yeah, correct. Just restate to be positive. Or actually just say in words, negative. So that means that tells you the F2 is acting to the right. You can say the words. Okay. Any other question? I think at least I will stop recording first. I don't want my file size to be too big. So let me stop the recording first.